Hello everyone, this is Stuart from N4L in the UK, and today I'd like to show you some of the functions provided by a PPA1500 compact power analyzer that are unique to our PPA series and really valuable to any academic, development or test engineer who wants to fully understand the power consumption of an AC input device. In this video, I'm going to focus on power measurement of a distorted load. So I've connected a commercially available switch mode power supply to a universal breakout box and have chosen the low power voltage connection point that's ideal for small devices and low power standby testing. And I've done this because it ensures that measurements don't include residual current flowing through the voltage measurement channel, which would be added to the measured current and therefore also the measured power. But let's start then. Even though we have the waveform, which people like because they're like oscilloscopes, let's start in the power analyzer mode, and you can see that we've synchronized on 50 Hertz or 50.025 as it is right now. And this is really important. I'll come back to that later. But you see there's no power because there's 0 amps. And that's because we've got zero blanking enabled. And that's common in lots of power analyzers because they want it to look like it's 0. And they also hide the absolute resolution or measurement ability at low current. But if I switch the low value blanking off, and this is in fact the default mode on our products, you can see that with my power supply off, I'm measuring between 30 and 40 microamps of current. And that's equating to low milli or microwatts of power. So it's exceptionally low, way below any standard that any product needs to meet in today's AC power measurement. And if I put a load on, you'll see we've gone from nominal 30 microamps to 30 milliamps, 1,000 times more current. So it means that we can see really low current confidently and with precision. And you can see that we've got totals and fundamentals for all the primary functions, so VA, power factor, voltage, current, frequency, and reactive power, plus phase angles. So voltage is 0, it's the reference, and the current is minus 309, so we know it's capacitive. You also notice that the voltage total RMS is bigger than the fundamental, which you'd expect. The current total RMS is bigger than the fundamental, which you'd expect. But often people don't expect the total power to be less than the fundamental power. And I can zoom into this and see it in more detail, and many customers will use these zoom in displays to be able to see numbers that they're interested in. And the numbers you can choose for zoom are completely flexible because you can choose any function you like. And then the red box selected items will be the items that zoom in. But let's have a look at that on the scope. We're seeing what we're familiar with, and that is a peaky current, and if I increase the load, then the current will go up. You'll notice that it always includes a complete waveform. We never clip waveform, which RMS products do. If you're RMS ranged on this, then we would possibly clip the waveform. So that's a bad idea for any modern power electronics, where the voltage or the current is usually distorted. And because people like oscilloscope functions, we can provide the type of function that people expect. So we can put cursors on there, and I've got the cursor set to 20 milliseconds. You can see I can change it or go back to 20. And that's going to be one cycle of a 50 Hertz waveform, and we've got some measurements between the cursors. But this image really illustrates the problem with any digital device that is based on a fixed window. And that is that you will not get a whole cycle in the window that you're measuring. There will always be some extra bits at the end of the cycle, and that will create modulation if you're measuring consistently window to window. Also, you realize looking at this type of waveform that phase measurement is always going to be limited. But phase measurement is really critical to power electronics, and we're going to look at this. So we've got some power measurement now. We've got this situation with a total less than the fundamental. Why is that? The answer to that is it's associated with harmonics. So many people will give you a harmonic bar graph. We can do that. Many people will give you harmonic tables. We can do that. But you'll notice that we have RMS voltage and its phase angle relative to the fundamental, then RMS current and phase angle of all the harmonics relative to the voltage again. Now, if we then look at that as an individual harmonic, we can see that the third harmonic is minus 127 degrees relative to the fundamental voltage. That means the power associated with third harmonic will be subtracting from the total power. And that is why in the power measurement you can see that the total is less than the fundamental. And this is just one of many functions where the PPA's ability to window correctly, to have a huge range, to sample without gaps, and to measure phase angle with extreme precision enables low power, power factor critical, or high power measurements very accurately. I hope this has been helpful. Thanks and bye for now.